Perfect, thank you. So as Akbar said, yes, I'm talking about the effects of shape and size on the granular mechanics in these very fun vacuum and microgravity environments. So I'm going to talk about this through the lens of the Strata 1 experiment. This flew on the ISS back in like 2016 to 2017. It was a year-long experiment. We had four vacuum tubes with varying fidelity of simulants that we used cameras to observe their behavior over the course of this year-long flight. And so this really was designed to help us better understand the dynamics in these environments by making those observations over such a long period of time with various forcing events coming from the ISS and the activities there. And that's really important for helping us understand rubble pile asteroids as one example. They are thought to have a lot of surface modification processes that would really be driven by the particle-to-particle interactions that we can observe in this experiment. And so observing that over a long period of time allows us to start to look into that. And specifically, we're interested in mechanisms such as the Brazil nut effect. So on Earth here, we see this the Brazil nut effect as a gravity-driven convection process that brings the largest particles to the surface of a container, or other things with lots of folks have looked into this of the rates, things like that. But we still see size sorting behaviors or size-dependent mechanisms on rubble pile asteroid observations and other scenarios like that. And so we look here to see, can we see the evidence of other versions of this, such as Morel et al. 2017 proposes a void space filling version of this Brazil nut effect. And so we're really trying to get at that. And to answer those questions, we really need to balance the complexity of the simulants we're using and their accuracy, right? So it needs to be accurate enough that we're doing something that's relevant to the environment, but it can't be so complex that we can't measure the data. And so you can see the sort of progression we're trying to fill here. So like you can start with a very simple spherical model, which is simple, easier to run, things like that. We just saw great examples of more complex versions of that. But if you jump all the way over to the right to the meteorite side, that's too complex. We can't quite see what's going on at the grain level. And so instead, we're going to focus, at least for this talk, on the spheres and shards in the middle there. And so we have color-coded by size, red smallest to green largest, glass spheres and shards. And so they're otherwise, we're just varying the particle size, the particle shape, and we can observe each of those. So that's how we collect the data that we're looking at here. So first, to go through the trends by the particle shape. So how you can read these graphs that I'll have, really you're looking for the overall behavior that's going on. And that's in percent coverage, which means how much of an image is covered by any one color or any one size of particle at any given point in time. And so how many of these particles can we see relative to the amount of tube we can see? And so what we see here is on the top, we see the shards that are much, much more active than the spheres, which are a little more calm, less dips and valleys and peaks and things like that. And so we're proposing that this is indicating that the irregular shape of the shards allows void spaces to form so that particles can move in and out of view, and we see those changes. Whereas the spheres, by contrast, might not have as much void space, and so you can't have as much motion in and out of view of the camera. We also have to put a little caveat there. We did notice that the red spheres, especially the smallest spheres, tended to cling to the surface of that tube. We're proposing this is likely due to triboelectric charging, and that tracks because that would be related to the surface contact area, as you can see in the little diagram below. But either way, the shards are clearly much more active, even more active than just with that caveat. So the next thing we look at is trends by particle size. And so this goes from smallest to largest. It's a little harder to read, but what we're seeing is that the small particles are really more likely to be moving in and out of camera view. They're more active overall. If we're seeing changes in coverage, yes, we see the larger particles sort of move out of view, but mostly we're seeing the small particles move in and out of view. And so this, as I alluded to at the beginning, is really consistent with that presence of size-dependent mechanisms. We see variations in the behavior based on the particle size. So the next thing that we did is we wanted to look at some of the tube characteristics and where we are in the samples. And so we binned the images. And in this context, that means we took each image of the tube and we broke it apart into 8 bins so that we could talk about what was going on relative to where each section, each bin is in regards to the tube. And so this, in this talk, I'll talk about macroporosity specifically. So we had something, we called it an intrapolator. It was a scissor jack that held the samples to be compressed as the experiment was being set up. But once it got onto the ISS, the experiment got up and running, that scissor jack retracts and allows for more space for the particles to move. What we notice when going through the images is that that added macroporosity, that added space for those particles to move, really is maintained throughout the experiment to at least some degree. And so what we can do is we can say, okay, let's now take those bins and plot them by increasing macroporosity from top to bottom. And so here we focus first on the spheres data, and you can see the first are omitted because that was not a good imaging area. But if you go down on the other bins, we're seeing a really clear increase in particle activity as the macroporosity of the sample is increasing. We're also seeing that the shards are overall active across all the bins. All of that motion we saw in the earlier plot of shape is uniform across the whole bin to some extent. Now, that is still consistent with the activity level increasing as macroporosity increases because those shards are irregular and thus, as we were proposing, more able to make those void spaces, which means it would have a higher macroporosity on average than the sphere samples either way. Now, the last thing I'll talk about is the forcing events. And so we looked at a couple different types of events here. So we had a mixture of slow forcing events, which are things like ISS reboosts or other events like that. A reboost is when the ISS accelerates in the direction of travel. It's been described as like a sledgehammer type event, but it usually occurs over the matter of hours, minutes and hours, sorts of timelines there. And we also look at a lot of more vibration-induced, very transient events, as in on the order of milliseconds to seconds. And a note there is that despite the fact that the microgravity environment on the ISS is technically just like a quasi-steady state thing, it's not perfectly 0G, we are seeing that the types of forcing events we're talking about are really what's dominating the interactions we're seeing. It's not the sort of steady-ish state global uniform forces that we would be seeing. And so here we see that this is an example of the same reboost in the shards on the left versus the spheres on the right. And they have vastly different reactions to the same event. So that tells us, and this is propagated throughout the various events that we look at. And so this is telling us that the same event can cause very different changes, and thus the sample characteristics make a difference in how the sample is reacting to these events. And since the difference is mainly particle shape, then that plays a role. Okay, so just to review, the particle shape, we are seeing a measurable change in particle behavior, even despite the triboelectric charging sort of disproportionately affecting the glass spheres. We also, again, found that evidence for the size sorting behaviors. We're seeing mostly the small particles moving in and out of view. And that together really starts to look very consistent with that void space filling version of the Brazil nut effect that I mentioned in the beginning. And so we're seeing this picture where the particle shape may be more influential for those large particles, such as the shards, so that they can create the void spaces. And then, but that regardless of shape, both the small particles, the small spheres, and the small shards are able to move in and out of those void spaces, regardless of their shape. And so that together, then the other thing that we're seeing is that the particles can demonstrate some sort of bulk resistance to change when external forces are applied. But that amount of resistance and the resulting change is dependent on the particle characteristics, like the shape, and on the sample characteristics, like that macroporosity, if that macroporosity is higher in the shards. And that is what I have. Thank you very much.